Okay, is the microphone actually working? Maybe. Okay, well, hopefully. Okay, great. So again, my name is Meredith MacGregor, and I am a second-year grad student at Harvard University. And today I'm going to be talking about a resolved millimeter emission belt in the AUMIC debris disk. Before I get too far along, I just want to take a moment to acknowledge all of my collaborators on this work. All of them are listed here, and many of them are actually in attendance at this conference. So I really organized this talk into three main segments. First, I'm going to start out by doing a little bit of a review of the birth ring framework of debris disks and how that framework actually explains the optical scattered light profile for AUMIC. Then I'm going to move into talking about some 1.3 millimeter observations from the SMA and how the results from those observations are actually consistent with this birth ring framework. And then finally, I'm going to talk about some new cycle zero ALMA observations, again at 1.3 millimeters, and how those are really giving us a much clearer view of the millimeter disk structure. Okay, so to start off, a little bit more about AU microscopy for those who are not familiar with it. It's a member of the Beta Pictoris moving group, so it's about 12 megayears old. It's fairly nearby at 9.91 parsecs, and it's an M star. So AUMIC, the debris disk around it, is really one of the best studied debris disks, mostly because of its brightness and its proximity. The circumstellar disk was initially discovered in coronagraphic images of scattered starlight. So you can see here in this image from Fitzgerald et al. 2007. What's very striking is the debris disk is incredibly edge-on. In fact, the inclination is about 89.5 degrees. Now, this bottom plot here is showing the optical surface brightness profile, so as a function of radius. And you can see that there's actually a knee or a turnover in this brightness profile. So there's a break at about 30 to 40 AU for AUMIC. This feature is also seen in the Beta Pictoris surface brightness profile. And these observations have really led to this uniformed view of debris disks that invokes having a localized belt of planetesimals, or what's commonly termed a birth ring. Now, I just want to point out that this birth ring theory actually assumes that the disk is pretty much dominated entirely by dust dynamics, and that there's absolutely no gas remaining in the system. So this paper by France et al. In 2007, they actually inferred a molecular hydrogen to dust ratio for AUMIC. And what they came up with was less than 1/30th to 1. So that really confirms that it's appropriate to assume that this disk is dust poor, and gas poor, and entirely dominated by dust. So birth ring theory. Essentially, we have a belt or birth ring of larger planetesimals that are actually colliding together to create these micron-sized dust grains in what's termed a collisional cascade. So you have larger grains colliding to create smaller grains, and then colliding to make even smaller grains. Now, the inner region of the disk is actually emptied out either by corpuscular and Poynting-Robertson drag or by grain-grain collisions. And then stellar wind and radiation forces actually blow out the dust grains from this inner birth ring to the outer regions of the disk. Now, in the case of AUMIC, it's an M-type star, so really more dominated by stellar winds and not radiation. So this birth ring would actually remain hidden in any infrared or optical images of the disk, because at those wavelengths, you're really only sensitive to these smaller grains that are getting blown out into an extended halo. So we really want to look in the submillimeter, where we're sensitive to thermal emission from larger grains that are actually going to be tracing the location of these large planetesimals. So as a result, we would expect the millimeter emission, or the location of that millimeter emission, to actually coincide with this break in this surface brightness profile. So this plot is taken from this paper by Strube and Chang from 2006. And this actually leads to a concrete prediction for where we should see this birth ring and the millimeter emission for the AUMIC disk, marked by this green line here at the knee in the plot, which is about 43 AU. Okay, so some actual observations. On the right here, I'm showing a plot that has two things in it. In color is the HST scattered light observations, and the black contours of the SMA 1.3 millimeter observations. The synthesized beam for these observations was about 3 arc seconds, and the RMS was 0.4 millijanskis per beam. Now, in actually modeling this data, we adopted a parametric modeling scheme and fit directly to the visibilities. And by fitting directly to the visibilities, we're not sensitive to any of the nonlinearities that are associated with deconvolution. So a little bit more about the actual results. Let's focus first on the left three panels here. Again, I'm showing the data. What's particularly notable here are these two bright onsae on either side of the disk, and that's indicative that this is really a ring with an inner hole. Then there's our best fit model, and then a residual image. Now, the residual image is made by actually subtracting the data and the model visibilities, and then imaging those again. So our best fit model has three parameters really to it. There's an R center here, which is the position of the belt, a delta R, which is the width, and then a total flux for the belt. And on the far right plot here, I'm actually showing a chi-squared contour surface. So this is the width of the belt, and then the center position of it. And these are 1, 2, and 3 sigma contour levels, with the plus marking the actual best fit parameters. And the takeaway here really is that these parameters are actually consistent with that prediction made from this birth ring framework. So we have a center position of 36 AU and a width of 10. Okay, so some new ALMA observations. We again observed at 1.3 millimeters, which is ALMA band 6. We had a 2-hour scheduling block. It was actually executed 4 times. But all the images and the analysis presented here, we actually only used the final of the 4th scheduling block. It had the largest number of antennas and the lowest precipitable water vapor, so we really got the best constraints on our model parameters. The RMS for these observations was 30 microjanskis per beam. The number of operational antennas was between 16 and 20. And our synthesized beam was 0.8 arc seconds by about 0.7 arc seconds. So if you remember back, the SMA beam was about 3 arc seconds, so this is really a considerable improvement. This image here is just a simple natural weighted image of the observation of the continuum emission. Again, you see the edge-on belt with these 2 bright onsae on either side, but now there's this new unresolved central source. So just a little bit more depth about our actual modeling. We are assuming an axisymmetric belt, and then we characterize that as an annulus with actually a radial intensity. And that is defined as the power law R to some power x. And defined within an inner radius, R in, and then an outer radius, R out. And then we actually normalize the entire flux of the belt to some parameter F belt. Now, in order to account for that new unresolved central source, we actually added in a circular Gaussian defined by a mean and a variance. And then we fit all of this modeling within a Markov chain Monte Carlo, or MCMC framework, which really allowed us to have a much more flexible modeling scheme and use different parameterizations. So the actual modeling results, again, I'm showing a data, model, and residual image. You can see that the residuals are very clean, so the model is actually a good fit. And this best fit model has 2 distinct components. So there's an edge-on outer belt, and that belt actually has an emission profile that rises with radius out to an edge at about 40 AU. And then there's an unresolved peak at the center of the belt. Okay, so the one overwhelming table of the talk. This is really just to show the range of parameters that we fit for in our models. There's 12 in total. To guide your eye, in red are the parameters describing the outer belt, and in purple are the parameters describing the central peak. So the next couple of slides, I'm going to talk about each of these components separately. So to start with the outer dust belt. Now, the position of the edge of this outer belt is really very well constrained out at about 40 AU. And you remember back, that matches closely with both our previous SMA observations as well as with the predictions from this hypothetical birth ring. The second point here is that our resolution limit was about 6 AU, but within that limit, it appears that the outer edge of this belt is actually truncated or cut off sharply. That's really reminiscent of our own Kuiper belt. Reasons for that could be some kind of dynamic interaction or initial conditions, but we really would need higher resolution observations to probe that in more depth. I also mentioned that we described the belt as having an annulus with a power law intensity. So our best fit power law index is actually 2.3 plus or minus 0.3. For a typical protoplanetary disk, you might assume that the temperature is going to fall off with radius is about r to the minus 0.5. So that actually implies that the surface density has to rise as r to about the 2.8, which is really not what you would expect for a typical protoplanetary disk. I just want to point out this paper by Kennedy and Wyatt in 2010. They actually discuss self-stirred disks, so disks in which there's actually planet formation going on within the disk. Now, the timescales to form a sort of Pluto-sized body within the disk are faster on the inner side, so the inner edge of the disk can actually appear depleted relative to the outer regions of the disk. However, the timescales to actually produce a Pluto-sized body out at 40 AU, which is where this disk is, are much longer than the about 10 megayear age. So clearly more investigation is needed. And then finally, we don't detect any asymmetries or substructure in the disk. However, our limits would still be consistent with having up to a Uranus mass planet within the disk. Okay, so on to the unresolved central peak. The real question here is what exactly is the nature of this central component? So the clear first guess might be that it's simply the stellar photosphere. However, if you use stellar models to predict the flux of an M star like AU-MIC out at 1.3 millimeters, the predicted flux is about 52 microjanskis. And the flux that we observe for the central component is actually more like 320 microjanskis. So really, the photosphere should be about 6 times fainter than our observed flux, and we can really rule this out. So the next possibility, AU-MIC is actually known to be a flaring star. But you'd expect a flare to have a fast decay time, somewhat on the order of an hour. And as I mentioned before, we actually have 4 executions of this scheduling block, and those span between about April and June of last summer. And the peak persists in all 4 of those scheduling blocks. So there's no indication that there's any variability in it. So we can really conclude that this must be some kind of thermal emission and rule out the possibility of it being a flare. Which leaves us with 2 really valid possibilities here. So one is that it's simply a hot stellar corona. One way to test this would be to actually map out the spectrum of that central source with the VLA. And the other possibility is that it's some sort of unresolved interplanetesimal belt. Now, since it's unresolved in our images, we can conclude that it must be within about 3 AU of the star. So if you do some rough SED modeling for a belt of dust that's within 3 AU of the star, the temperature you get is actually consistent with what you might expect. An important constraint from AU-MIC is that there's not actually any observed excess in the SED, shortwood of 25 microns, so that places a pretty stiff constraint. So a little bit more about this idea of a stellar corona. What I'm showing here is a plot from this new paper from Steve Cranmer that's actually just been submitted. So this is showing synthesized radio and millimeter spectra for a coronal heating model of AU-MIC. Now these gold and black arrows are previous VLA limits, and this point right here with the error bars is actually our 1.3 millimeter ALMA flux measurement. Now all of these models actually match a previous X-ray luminosity measurement for AU-MIC, and the difference between these 7 models is really in the structure of the coronal loop heating model. So the size distribution of the loops and how fast the foot points of those loops are moving around. All of these models actually match with these previous VLA limits, but only the thick black line, this one model here, actually matches our 1.3 millimeter flux. So the real takeaway here is that it actually is plausible to explain the flux from the central source entirely due to a hot stellar corona. So if that's the case, how might we actually be able to distinguish between these 2 possibilities? So I actually did some higher resolution simulations. These are, again, in band 6 and use the ALMA cycle 1 configurations. So on the left here, I'm showing a model which incorporates an inner belt that extends between 2 AU and 3 AU. And then on the right is the same model, except instead of having an inner belt, it simply has an unresolved stellar corona. And you can see that we can actually, even with almost like a 1, clearly resolve a belt that's within 3 AU of the star. So you see these 2 bright on site from the inner belt and then from the outer belt as well. So there's actually an accepted almost like a 1 proposal, which Meredith Hughes is the PI on. So again, even with almost like a 1 and a beam of about 0.25 arc seconds, we should be able to resolve it if it is in fact a belt that's within 3 AU of the star. So that brings me to the summary. So I started off by actually doing a brief review of birth ring theory and how that actually explains the AU-MIC scattered light observations. Our initial observations with SMA at 1.3 millimeters actually yield results that are consistent with this birth ring theory. Our new ALMA observations at 1.3 millimeters give us a much clearer picture of the millimeter structure of the discus, and actually reveal that it has two distinct components: this outer belt and then this central source. Which leads to the final point that with future observations with both ALMA and VLA, we should actually really be able to determine the nature of the central component definitively. And with that, I'll take any questions.
Questions?
In the back.
Oh, back here.
Michael Liu. You mentioned you did not detect any substructure in the millimeter observations, but that substructure is robustly detected in the optical and the near infrared. Have you thought about the implications for the nature of the substructure because it's undetected in the continuum?
So a little bit. It's interesting, I think, that a number of these millimeter observations have not detected substructure that has previously been seen in the optical. I think it would be interesting, again, to get further observations with ALMA to see if that really is consistent. I know a number of times people have pointed out that in this image there's actually one side appears brighter than the other side. But if you refer back to that initial image I showed of the data model and residual, there's no significant residuals. And those residuals are imaged the same way as all also the data in the model, and those are 4 sigma contours. So there's no significant indication of any asymmetry. So.
Mark?
Your cycle 0 observations were taken in TDM mode rather than FDM mode, which meant that you couldn't search for CO,
Right.
which, although it wouldn't have made much of a difference to these observations. Are your cycle 1 observations going to be able to search for CO?
Yes, I think that would be best referred to Meredith Hughes, since she's the PI on that proposal, but I believe, yeah.
Yeah, Meredith is nodding yes.
We'll get observations at similar resolution to this, in addition to much higher resolution observations, and the one at this resolution should be able to detect scale.
That's great.
Okay, time for one more. Mark?
I just wanted to follow up on Mike's question there. So we saw in Sam Lawler's talk that in the Kuiper belt, although there is a significant amount of bodies in the resonant population, they certainly wouldn't be detectable if you just looked at the emission. So perhaps it's not a surprise that we don't see these kind of structures in the submillimeter here that we do see in the optical.
Yeah, that's an interesting point.
Okay, James.
Quick question was, could you speak to the prospects for resolving vertical structure in the disk?
Right, so that is, I think, was certainly the intent of Meredith Hughes' almost like a one proposal. You can see here that the beam is actually about the same thickness as the disk. So in our cycle 0 observations, we can't actually say anything conclusive about the vertical structure. But I think in cycle 1 that should certainly be a possibility. So that will be interesting to see what the results are of that.
Maybe I'll give Meredith one word on that.
Which word should I choose? So yes, that's the intent behind our cycle 1 observations, and the exciting thing about the cycle 1 resolution that wasn't possible at cycle 0 is that we'll be able to resolve several times below the scale height that's been measured at optical wavelengths. So we'll be able to see if the ALMA scale height, the millimeter wavelength scale height, is comparable to or smaller than the scale height at optical wavelengths, which is very interesting from a physical point of view.
Great. Okay, let's thank Meredith again.